Hi everybody, I'm Mehdi. Welcome to my channel. I'm excited to explore today the fascinating topic of single crystals and polycrystalline materials with you. So let's get started. Let's define single crystals. A single crystal is a solid material where the periodic arrangement of atoms and totally the crystal structure extends uninterrupted throughout the entire specimens. Single crystals show uniform physical and chemical properties in all directions due to their consistent atomic arrangement. They are often characterized by distinct shapes and well-defined phases. For example, diamond single crystals used in abrasive materials due to their exceptional hardness, common in cutting, grinding, and drilling applications, or single crystals for turbine blades, employed in gas turbine engines to enhance performance and temperature resistance. The single crystal structure helps in reducing the risk of fatigue and improving creep resistance. How about quartz single crystals? They widely used in electronics, for example, oscillators and resonators, and optics due to their piezoelectric properties, important in manufacturing of watches and clocks as well. So, the unique properties of single crystals make them valuable in various high-performance applications across industries, highlighting the importance of understanding crystallography in material science. So, when it comes to polycrystalline materials, they consist of many small single crystals known as grains that are randomly oriented. Most engineering materials fall into this category. How about grain structure? Each grain represents a single crystal with distinct boundaries separating them. Sizes can vary significantly, typically ranging from 1 nanometer to 2 centimeter. So this range corresponds to a few millions of atomic layers. A figure illustrating a microstructure showing both large grains and small grains can help visualize the diversity in grain sizes. NBHFW plate with an electron beam well demonstrating the fine microstructural details of polycrystalline materials. The mechanical properties of polycrystalline materials such as strength and ductility are influenced by grain size. Generally, smaller grains can increase strength throughout mechanisms like grain boundary strengthening. How about the applications? These materials are used widely in engineering applications, including metals, alloys, ceramics, and some polymers, where the balance of properties is critical. Well, let's explore more with the definition of anisotropy. Actually, anisotropy refers to the phenomenon where a material's property value varies based on the direction of measurement, particularly evident in crystalline materials. Anisotropy is most commonly observed in single crystals, where the arrangement of atoms leads to directional dependence of various physical properties. For example, modulus of elasticity in BCC-IR. The modulus of elasticity demonstrates anisotropic behavior in BCC-IR. E equals to 73 gigapascal diagonally, but E of H equals 125 gigapascal. It means that the stiffness of material varies significantly depending on the direction in which it is measured. So let's focus on unit cell visualization. A visual representation of the BCC iron unit cell can help illustrate the atomic arrangement that contributes to its anisotropic properties. Understanding this thing is crucial for applications where directional properties are critical, such as in structural components, aerospace materials, and electronics. Polycrystals consist of many small grains, each being a single crystal. The overall properties can show isotropy or anisotropy depending on the orientation of these grains. If the grains are randomly oriented, the material's properties tend to be isotropic. For example, the modulus of elasticity for polycrystalline iron can be expressed as E equals 210 gigapascal. In this case, the material behaves the same regardless of the measurement direction. If the grains have a preferred crystallographic orientation, for example, due to the formation processes, the properties can become anisotropic. It means different directions will yield different values for properties like strength, ductility, and modulus of elasticity. Understanding isotropy versus anisotropy is essential in material selection and design for engineering applications, specifically where mechanical performance and stability are critical. Now, let's define polymorphism and allotropy. So, this thing refers to the existence of two or more distinct crystal structures for the same material. Usually, we use allotropy for pure elements and polymorphy for the compounds. Now, let's explore some examples. Titanium exists in two forms: alpha titanium with hexagonal close-pack structure and beta titanium with body-center cubic. The next example is carbon exhibits different forms: diamond with a tetrahedral bonding resulting in a strong rigid structure, graphite which is a layered structure with weaker van der Waals forces, allowing for slip between layers. In addition, iron. The iron system demonstrates, this behavior at various temperatures. Liquid iron, so melting point at 1538 centigrade degree. We have body center cubic delta Fe structure, which is stable above 1394 centigrade degree. We also have face center cubic structure, gamma Fe, which is stable between 912 centigrade degree and 1394 centigrade degree. In addition, we have alpha Fe with BCC structure below 912 centigrade degree. The existence of multiple crystal structures in the same material can remarkably affect the mechanical properties, phase stability, and applications in various fields such as metallurgy and material science. If you enjoyed this video, please like, share, and subscribe for more engaging content in material science and engineering. Your support helps me continue exploring more topics together. See ya.